right. Find out together here, but I think I am live. Give me a moment here, Twitch, to verify. Maybe. Yes. Okay. I think we're in good shape. Weird hearing myself echo. That'll work. All right, I'll give it a moment for the Twitch feed here, and then we will start the show. Hello there, Twitch. I do see you. Got a couple people saying hi. Somebody says, you're hearing some people miss the announcement in class because of no ping. Let's see, what announcement? Grading bug. Grading bug, reverse engineering's live. Last thing in announcements was something about meme grades. I don't know if you want to clarify on the ping. What was missed? No camera today, unfortunately. So I guess you're just functioning delayed. So I don't see a response yet. I'm going to go ahead and start the show. We'll see what's happening here. Somehow you all are chatting and Twitch says there's 0 people in the room. The announcement that today was fully online. So I definitely said it in class last week. It was posted in the announcements at least a little bit. If you are in class, I guess you all can throw it on the projector and watch this live. I'm not sure. Not sure what to say about that one. It's been in the announcements, I think, for a little bit. Okay. So today is 9/11. We're in week 4 of CSE466, and we are talking about reverse engineering. So I am not in class. I am traveling with the university, but I will be back in Arizona next week, so things will be a bit more normal. Memes. So we had quite a bit of memes over the past week. We had memes about program security as you all were kind of wrapping that up. One of the interesting things, of course, is more people move through kind of the complex exploitation stuff, which means that this first meme here with NX being enabled, it turns out, as it was mentioned in one of Jan's lecture videos on memory corruption, that NX does stop the stack from being executable. However, if you do have the ability to call mprotect, you can make the stack executable. For one of the challenges in the FizzBuzz, this was a relevant point. Hopefully you found that. It wasn't meant to be hidden. There's a function in one of those challenges that's named like mprotect stack or make stack executable. And so that was something that you were supposed to be able to discover and hopefully utilize to obtain the flag. Other memes, we got a couple just dunking on me here. The typical Robert experience, right? With the challenge is easy, just leak the flag, and we can't figure out what to do with the primitives that the challenge has. But you've actually done these things many times. Somebody does say here in Twitch that they solved all 3 challenges without ROP, which is fantastic to hear. There definitely is a number of unintended solutions for those FizzBuzz challenges that use ROP, but the intended solution did not utilize ROP at all. And in order to do that, you did have to kind of follow along with this meme right here, where we need to start leveraging, for instance, string copy buffer fizz. We need to think about how we can leverage what the program does to obtain a leak that is useful to us as an attacker. And while it does sound like a lot of pain, a lot of time the answer is in the man page. It's a running meme, and we're inevitably going to open up a man page today as well. Last week's stream was a bit more intense than this week's stream. I'm honestly quite tired. We'll see where we go. But we did get to make the cool file, which was a nice, enjoyable moment we all had together. Other memes, kind of segueing from program security over here to reverse engineering. Reverse engineering was supposed to go live on Friday. I think it actually went live on Saturday. There was just some things to get sorted out. But it did go live. It is reasonable. It's running for 2 weeks. I'm not going to give you the day. We're just going to kind of roll with it. And if you have grievances, let me know. Outside of this particular class lecture, we'll deal with it there. But right now, there's a whole nother week to 10 days for you all to work on it. So I think we're in pretty good shape. One of the things that you can do, and this is true not just for memory corruption, but it's also true in GDB, and a lot of students do this, is for whatever reason, early on, people avoid using GDB. They're scared of it. It's this intimidating tool, but it's insanely powerful. And one way that you can avoid GDB is by just leveraging for loops and sending in a steadily increasing number of bytes into a program. That will work. That will not work on things like FizzBuzz. And to be completely honest with you, if I have the time, I would do the best I can to make that not work in every challenge going forward as much as is reasonably possible. But if you did it and it got a flag is flag, more power to you. I just need to work harder to make that not work. Now, specifically talking about reverse engineering, we are working with tools that we might have been able to use in memory corruption, but you are definitely using in the reverse engineering module. So now we're using tools like IDA as well as GDB. It's totally fine if you use IDA or Ghidra or you prefer Binary Ninja. I myself prefer Binary Ninja currently, but I will try and do any static analysis in IDA or Ghidra since both of those are a bit more prevalent as far as what students use, and I want to show things that are useful to you. But one of the problems when you're working not specifically with IDA, but with a decompiler in general and doing static analysis is types. And so this meme here says, hey, I found this array that I'm interested in IDA. IDA represents it as a string. That's fine, right? A string is an array of characters, so it's a character array. And IDA thinks that it's 2 characters long. This sounds like pain now, right? This is probably not what's really going on. You'll find that this is the case a lot of the time when you're looking at static analysis tools and you first, open up a binary and hit tab. However, it's not that difficult to update the type information in a decompiler to get it to start representing things a bit more correctly. The way that you use or you're supposed to use a decompiler isn't just open up a binary and hit tab. It's open up the binary, hit tab, look at the function, start fixing up the types and names and things and try and get that decompilation to look a bit more like source code. Everything that these tools show you when you initially hit tab is going to be a best effort representation. It is going to get stuff wrong, but that doesn't mean that it's not useful as kind of a launching off point, at least initially. Here we have Yansanity, which I believe is the very last level of Rev, or at least the old last level of Rev. We take a look here. So we used to have Yansanity was the level, I think 22.0, which is a very unique challenge for this module. Because you have to reverse engineer Yan85, which we've been doing for several challenges if you're at this point. And write your own custom shell code to get the flag, but there's a twist. And the twist, I don't think it's a big spoiler here, is you have to do this blind. And what I mean when I say blind is Yan85 is its own instruction set with its own assembly instructions and bytes that turn into assembly instructions, and we have to figure that out. And the encoding of those assembly instructions is different in every challenge, but you can pull that out using static analysis or GDB. You can find it in the binary. In the Yansanity level, this is randomized, the mapping of bytes to instructions. This is randomized at runtime, which means you cannot use, and it uses the C or the flag as a seed. And so that means we cannot use IDA, we cannot use GDB to pull out these values. Instead, we have to put in a lot of time, effort, and thought into what do we know about Yan85 and slowly reveal small facts about this particular instance of the challenge to gain small little footholds and reason our way until we discover enough of the instruction set where we can obtain the flag. And so Yansanity is a pretty famous set of challenges where it's a blind exploration of the Yan85 VM. We also have this meme down here about memcompare. This one confused me for a little bit. It says 0 and true, corporate needs to find the difference, and memcompare says, hey, 0 and true are the exact same thing. This is, when I was kind of going through the memes, I wanted to take a look at it, because I was like, well, I don't think that's true. Like, the return value of memcompare is not a truthy value. And if we open the man page, of course, and look at return value, it says memcompare returns an integer less than, equal to, or greater than 0 if the first n bytes of the needle S1 is found. Respectively, less than, to match, or greater than the first n bytes of S2. You'll find this pattern of comparison functions returning either a negative, 0, or positive return value, representing a comparison, in a number of comparison instructions. Like, what's really going on here in the implementation, if we were to think about it, is this is essentially subtracting the two strings. And so if the S1 is larger as bytes than S2, we would end up with a negative value because we're going to subtract S1 from S2. And that would imply that S1 is, let's see, make sure I'm reading this right, returns an integer less than 0. So we're taking S2 minus S1. It's subtracting strings because everything is bytes, so we can do things like subtract strings, which is why you get a negative 0 or greater than 0 value. And that informs you if these strings are the same thing. So I wouldn't necessarily say that 0 and true are the same thing, but 0 is the yes, this matches value from memcompare and string compare. Lastly, we did add some new challenges, not as many as I'd like, but these seem to have been received pretty well. There's a small number of additional crackmes that are doing some like bit twiddling. Hopefully it's something that you may have not seen already, especially if you have done the earlier crackme challenges. But kind of the more interesting set of challenges, in my opinion, is the cows and bulls family of challenges. Now, I think this is a much better way of practicing the skill of reverse engineering, because this is a series of challenges that are completely different from the crackmes. It's completely different from Yan85. It is its own unique binary with its own unique behaviors. And so in order to obtain the flag on these challenges, you need to understand something that is foreign and unlike anything that you've seen before, which is really how you practice the skill of reverse engineering. I am talking a bit less on stream about Yan85 than I have in the past, but that's because reverse engineering is the act of figuring out how a program works. I don't feel that bad about it, though, because this class has about half the number of Yan85 challenges compared to previous iterations. So I think you can spend a little bit more time on each challenge figuring out how they work, rather than having twice as many challenges and kind of getting sped ran through it. The cows and bulls challenges do have a value that is fairly important if you have taken a look at them, and that is the entry ID. I'm not going to spoil what it is, but the entry ID plays a pretty big role in helping you understand how this program works once you open it up and start taking a look at it. And the kind of progression here is we explain, or we provide a link to how Cows and Bulls works. It works very similar to, for instance, Wordle, where you're guessing a number and you either guess the correct number in the wrong spot or the right number in the right spot. You get some feedback, you get to guess again. Now, when presented with this game initially, you probably think, hey, I need to win the game to get the flag. And that may or may not be true, even on the very first challenge. Because one of the messages that the challenge says is, yeah, you guessed right, you found the right number, but that is not enough. Now, the game does not tell you what you do need to do. Instead, it is your job to reverse engineer the logic of the game to find out what is enough for you to obtain the flag. Now, once you do find a workaround for whatever the first roadblock is, the next challenge introduces a twist on the roadblock, and so whatever workaround you found is probably not enough for the next one. And this progresses to where the amount of work that you need to reverse engineer how the game is figuring things out becomes a little bit more complicated and a little bit more complicated. And you have to practice your reverse engineering skills both in IDA and GDB, as well as your ability to forward engineer a solution to problems that you may discover via reverse engineering. Logistics. The grades page, including memes, should be live as far as I'm aware with both modules, the program security as well as reverse engineering. The memes grades should be calculating correctly right now. If anyone believes that anything is off there, please let me know. As far as I'm concerned, it's off my to-do list. The next module, ROP, will launch on Friday. Not tomorrow Friday, but 1 week from now Friday. So we do still have some time here to focus on reverse engineering. I'm not going to add any more reverse engineering challenges to this module. I did say last week that I was working on some things, which I was, and I have some challenges, but I'm not going to add them halfway through the Rev module. We may see them later in the semester in our program security or system exploitation module. We may see some more Rev-focused challenges at kind of that midterm or final module that we launch alongside the course. It's kind of a culminating challenge. I did say last week I was going to try and get some grade slides. I don't believe we were able to get any up on Tuesday, and I unfortunately have not had time this week to produce them for today. I will be back, as I said, next week, so we'll definitely have some pretty graphs to talk about how the class did on the first module sometime next week. Again, if there is something that you are particularly interested in, please let me know. We'll take a look at it and try and get it on stream. So my plan today for what we're going to demo, I took a look at what Michael covered and kind of what I could add to that. I'm more of a dynamic analysis person, but I wanted to show some tips on how we could utilize IDA to inform how we GDB. Michael used something called PIE run, which is a Jeff functionality, and then PIE break. And that is a very cool workflow, except that it doesn't work very well if you are also using pwn tools to launch GDB. And so I'll show a way that we can kind of leverage pwn tools with ASLR and Jeff and still be able to deal with PIE and kind of these randomized binaries. Hopefully, Michael did do some rebasing of addresses in a static analysis tool. We can take a look at that. And how we can use one tool to inform us about the other. As far as how do I demonstrate reverse engineering, I asked someone in the pwn.college community to recommend some CTF archive reverse engineering challenges. I honestly don't know what they are. I just have a list of challenges to find and open. My plan, unless you ask for something else, is to open up a couple Rev challenges and kind of see what is going on and see if I can manage how many I can solve in the whatever remaining time that we have. And of course, if there is something that you want me to do, I'm more than happy to drive the class time in the direction that you're interested in, as long as it isn't tell me how, for instance, Yan85 works. When I asked what you'd like to see, I'm not going to reverse engineer your challenges for you. If you do want help reverse engineering your challenges, definitely go to office hours, go to something that's off stream. I will be a little bit more helpful there rather than streaming wide across the internet. Somebody asks, why pair GDB with IDA when you can just debug with IDA? And that's a good question, I suppose. If you prefer using a GUI tool, let's launch. Somebody asked about on the Discord here, I think Tangled Ticket Hard. So let's run that. And I always start challenges in practice mode. And what we'll do here, switch to the workspace. Somebody says, better do it locally. We'll find out. Well, you know, students have to do this on the dojo. It's probably better if I do it on the dojo so I experience what the students experience, right? So we're going to open, looks like Baby Rev level 2.1. I should change the name of that binary. I'm going to open it up here in IDA. We will hit tab, and this is typically as much work as people do when they're working with a static analysis tool, to where it's kind of a meme. Just double click the binary or feed the dragon in Ghidra, hit tab, right? Look at the decompilation and go from there. And so the first thing I want to look at on the left-hand side is what symbols do I have? But one of the things that should be true for these challenges is the binary here. It is an ELF, but the 2.0 versions have symbols. The 2.1 versions are stripped. A stripped binary is a bit more painful to reverse engineer. What that means is we do not know for instance, function names or variable names, any extraneous symbols that were in the binary have been removed. And so that makes reverse engineering and kind of reasoning about where you are a little bit harder. For instance, I would bet that main is not really here in the binary, but IDA has named this main because it is being called by libc start main. And we think that the entry point to a process is always main. There's actually stuff that goes on before main, and the thing that calls main is part of loading a ELF file into memory and executing it. The thing directly above main is libc start main, and so you'll always have this function interaction or backtrace as you go into main. And so we can use, IDA likely uses that as a heuristic to determine what function is main, or where main is. All right, now before I look through the source, a great thing to do is to just run a binary and see what comes out the other side. This challenge says it's a license verifier, blah, blah, blah. However, we can do anything. Before we can do anything, we must verify we are licensed to read the flag file. The program consumes a license key over standard in. Each program may perform entirely different operations on that input. We have to figure it out and provide the correct key. So let's give it some input, and it says checking the received license key, and it just gives me the feedback that it is wrong. So we've played around with it. I could run this a few times. I could look and see what is going on in here. I'm probably not going to learn a lot since I just have I'm thinking about how this program is probably structured. There's just some type of mangling or modification. Then there's a comparison, and it's very unlikely I'm going to be able to elicit a different behavior by guessing and kind of seeing what the program does. So now that I have a mental model of what this program is doing by playing with it, we can take a look at IDA. It says ready to receive your license key. It's going to read from standard in into this buff. I'm putting my cursor on buff, and you'll notice that it highlights everything so I can see where buff is used. Another thing that is useful, maybe not necessarily useful in this challenge, is to be aware that you can hit X, and this X is a shortcut for cross references. And that this shortcut is pretty common across all decompilers. You can use X to find everywhere that the symbol that I have my cursor on is used in the entire binary. And so we see there's 4 uses right here that are highlighted in yellow, but when I hit X, there's actually 5 uses. So there's another one that is off of my screen. So I have the 21, line 24, 25, 26, 21, 24, 25, 26. It turns out there's another one. It's in the same function. Right down here on line 29. That's not super interesting for this variable because this is a local variable. However, if I was dealing with something a little bit more complicated, then this X cross-referenceability allows me to jump around and see how things are used. It'll definitely be useful in challenges such as like the Yan85 stuff, where you may have values being passed around or globals being referenced from all over the program. It's a very quick way to see everywhere that a function or variable is used. So a symbol is not just a variable, it could be a function name. For instance, this is memcompare, and it's only called once right here. But back to the task at hand, what is going on? It's going to call read. It's going to read, looks like 5 bytes into a buffer. I then get whatever this is doing. It says byte 2 of buff goes in V3. V5, which is 0, is going to go into byte 2 of buff. And I did like this byte 2 thing isn't clear what this is. I still don't know exactly what it is. And it's going to be common in this course when you look at these type of things to see something that you're not familiar with. Now this is in IDA, and so I would just Google it. So let's say IDA byte 2. There's this byte 2 function. We're going to trust the Google AI. This is a little bit scary, but let's find out. It says the byte 2 function in IDA is a decompiler helper macro used to extract the 3rd byte, index 2, of a multi-byte variable. It's not a function in the traditional sense, but a macro to make decompiled code more readable. And so what this is saying is the 3rd byte, the byte at index 2 of buffer, will be stored in a local variable, V3. Right here, it says V5, which if we look at the decompiled code, is 0, is going to get stored in that spot. We then have a different function here, or IDA macro, low byte. I don't know what low byte is. So let's IDA low byte. Did I misspell it? L-O-B-Y-T-E, L-O-B-Y-T-E. I now know it is a macro. Low byte takes a 16-bit value as input and returns the least significant 8 bits. Okay, so it's as the name or the mnemonic here kind of implies, it's taking the low byte of this buffer, the least significant byte of this buffer. Somebody says, I guess low byte is the last index byte. Well, I don't like first and last. And the reason for that is people get confused with indexes. Okay, so they corrected. Twitch chat said, I guess low byte is the last index byte, and they changed it and updated their message here to LSB, which I'm assuming is least significant byte. And I would agree with that. Like low implies it is the lowest, least powerful byte. So it's going to be the least significant byte, which when we think about how numbers are stored, that is the first byte of this byte array, which is only 5 bytes long. Now, one of the questions here in Twitch chat also was, what is this ULL, right? Why do I have this? Well, decompilers have to guess at the types of things, right? Decompilers are working with stuff that looks like this. They're dealing with assembly instructions. And in assembly instructions, we don't have types. Everything is just bytes moving around in memory and registers. So I don't know if these bytes are a string, or these bytes are a 2-character array, or these bytes are a 500-character array, right? That's all up for a kind of interpretation and based upon how we see these memory addresses and registers being used. Like here, I see read being called. I know that the second argument to read is a pointer to a buffer that we're going to read into. And so that's how I can reason that buff is, let's see what type IDA thinks buff is. If you have your cursor on any symbol, you can hit Y for type. And this allows you to change the type declaration of what you are working with. Now, when I look at buff, if I'm reading into a location, I'm going to say claim, and I don't know this is true, but what I'm thinking when I ran this program is it takes some character input. I'm going to treat it as if it's a character array. So I actually want to change buff. I don't think it's an int. I think it is a character array of, well, we're going to say 5 bytes. IDA says the new variable size is bigger than the old one. It may overlap with other variables and destroy them. IDA does not like that I want this to be an int. So let's double check here. This buff is at RSP plus 22. V5 is at RSP plus 26. And V5 is being used right here. So what I'm seeing here is RSP is the bottom, plus 22. We write in the direction of R. What I want to know is what is in front of this buffer, right? What is it when I change this to a character array that IDA is very not happy about? Right? This sounds like a scary message. I'm going to just destroy a local variable, right? Well, if we go up to the top of this function, we see IDA thinks that buff starts at RBP minus EH. This H suffix implies it's a hexadecimal number. We can change this to a decimal number. See if I remember how. We right click. What do you do? You right click on a number, bam, and you can say, I think it's D, H, D, H. Okay. So you can change the type. It turns out 0 is 0. I need a number. There we go. A number that is large enough to where we can see the difference. Yeah, somebody says I can't change the comment. I can't change the comment using this H shortcut, which is true. This is a comment, not a literal. But like this number here is hex 28U. This U implies it is an unsigned integer. And what that means is that this value will not be negative, right? A signed integer, or we'll say byte. Like IDA thinks this is an unsigned integer, but if this were an unsigned byte, it could be any value from 0 to 255. If it is a signed byte, it could be any value from negative 128 to 127, to positive 127. And this U implies that it's an unsigned value, right? So I can get 40 decimal unsigned, or I could get hex 28 unsigned. It's the same numeric value, just a different way of representing it. Now, one of the questions here in Twitch chat is, what is ULL? Well, we have the U. The U implies it's unsigned, as I said. The LL is a shorthand in IDA for long, long. And this is telling us what is the type or how many bytes are being used to represent this value. And so when I hover over it, it says this is just some n, it's some constant here. It is an unsigned int 64. A long, long is 8 bytes in length, which is equivalent to an int 64. And so what this is, this little suffix stuff next to the number is quickly informing me of the size and representation of this data. Twitch points out that I should pay attention to the fact, and this is true, that the decompiled types are not correct. I think not that they are wrong, but they're not necessarily correct, right? It's a best effort at kind of predicting what the types are. Now, I really still believe that this buff is a character array of at least 5 bytes. And the reason I say that is we're reading 5 bytes into this. And so it doesn't make sense that this isn't 5 bytes. But what is in front of this, if buff is at RBP minus EH, and it's 4 bytes in size, take E hexadecimal minus 4. It gives me A, which is 10. So I have 10 bytes left until I get to RBP. And IDA thinks, RBP minus 10, that V3 right here is a character array, is a character. Why does it think it's a character? Well, let's see how it's used. Oh, it's being used down here as a low byte. Now, this is where when people say, hey, my IDA thinks that it's an int, or IDA thinks my character array is only 2 characters long, you have to be smarter than the decompiler. Now, we could observe this in GDB and see how this is being used. But what I think is going on here, because these are right next to each other in memory, is buff is a character array of at least 5. IDA's like, do you know what you're doing? I'm like, leave me alone, IDA. We are doing this. Right? And now IDA is grumpy because this doesn't match what IDA thinks is going on. What I really want to do is make this go away. I think this V3 is part of this buffer array. That's what I think is going on. Somebody says they think it's 6 bytes because of int 16. Int is 4 bytes and int 16. So this is what's in front, though, right? Because we write in the direction of RBP, right? We write up. And so if this is EBP minus H, we should be moving in this direction towards V3. Do you... Okay, Twitch says no. Twitch says I don't know how the stack works. Okay. Am I functioning on a delay? What do we got here, Twitch? RSP points to the bottom of the stack. When you're writing characters, you write in the positive direction. RSP is less than RBP, or RSP is less than RBP. Going once, Twitch. IDA is misleading, but it shows it in the direction that it writes to them. Okay, so this is an IDA-ism is what you're saying. Do I have the ability to undo then? IDA just doesn't understand how the stack is laid out? That would make me very sad. And I would be very surprised if that was the case. Control Z, bam, bam, okay. So then what I want to do is I want to make V3 a character array, and you're saying that would flow into buff. Twitch says yes. Okay, so let's make V3 this makes no sense then. V3, a character array of 5. It says it wants to mess things up. And it's saying that that doesn't add up. That should be an int, which is 4 bytes. That should be 5 bytes. I don't get why IDA is not happy with that. Do you know how to combine these by chance, Twitch? I could double tap the var to see the stack frames. Bam, bam. Okay. You have buff here. Okay, so I want this var A then. Like the point is that whatever is after buff, that 5th byte has to be part of buff. If I make it 6, IDA starts being mad, but it doesn't make sense. All right, so we got that. Does this look more reasonable? Well, that didn't do anything. Char 6, come on, IDA. Okay, IDA's not mad. Let's go back down and see if this pseudocode stuff cleans up and makes a bit more sense. So we're going to read into 2 bytes into buff for 5 bytes. Okay, well, if we're going to do that, then I want buff to be like 7 then, don't I? Because I need to be able to account for that. No, IDA really just like 6. Okay. I want the buff to be 8. We'll just eat all of them. IDA just doesn't like odd numbers. I mean, it kind of makes sense. Okay, so I'm swallowing all of this as a character buffer. IDA thought things were ints. What does IDA think if I make everything into a giant character buffer? Okay, now since I've informed IDA of the types, and I knew it had to be more than 4 because this thing was reading in 5. All right. So what I really have here is a character array where the 5 bytes from right here are being read in from standard in. I have this buff 0, which is behind where I'm reading in. It's going to hold the 5th byte. I'm just going to like envision this as a temporary slot, right? And so we're going to hold the character that's at buff index 4 in this temporary slot of 0. We're then going to take whatever was at index 6, place it in index 4. We're going to take the character that is in the temporary slot and place it in index 6. And so by fixing up these types, this looks a lot more sane than what it did before. Earlier, we had some weird V value being set to 0, and we were like moving 0 onto this buffer that held our input. But once I used IDA and fixed up the types, and there's probably a better way of doing the types here. Like I would think that we could make this into 2 bytes. Oh, wait, I got to do that. Bam, bam, up here. Make this into, and it will let me be 2 bytes. Yes. And then this, I would want to make it be 6 bytes as a character array. Is IDA happy now? IDA is very not happy because that's 8 bytes, but I'm separating them from each other. I'm going to name, I can hit N to rename this, and this is my input buffer. And I'm claiming that this thing, I'm ignoring the red because I think IDA is being a silly goober. We're going to call this temp slot. And really, that doesn't even need to be an array because we're indexing it at 0. So let's make it just a char. IDA is still not happy. IDA's just never happy. But when I do this, this is why we prefer GDB to IDA. No, like static analysis tools do have a purpose. Like I can knock them, quite a bit, but it's partly in jest, right? Whether it's Ghidra, whether it's IDA, whether it's Binary Ninja, it's just a different way of thinking. Like if you're trying to reverse engineer some large, complicated project that you're not familiar with, you definitely want to use a static analysis tool. You'll spend hours over here fixing up the types, trying to make this look like proper C code. Like that is how you tackle a very large project. You're not going to be able to understand a large, complicated program by just looking at it in GDB and staring at assembly. Like, even if you understand assembly real well, it's not a very good way of getting that high level view. Somebody here on Twitch is saying, yeah, for the easy challenge, it's way better to just watch things happen in GDB. And like, you could totally watch this interaction happen stepping through GDB, right? This is some type of byte swap that's going on here. We definitely see it in IDA after I change the types, and you would definitely be able to see that in GDB by stepping through and watching how the input buffer is changed, right? Both of those approaches would be valid. But we see that I used IDA, and by fixing up the types, I was able to produce some C code that looks a little bit more reasonable. And I now have an idea of what's going on. And you should type things so that they make sense to you and name things so they make sense to you. That is primarily how you get the decompiler to produce higher quality output. Now, one of the things that I said I wanted to show was how do we deal with pwn.debug, PIE, and pwn.tools gdb.debug. How do we make that make sense alongside these binaries? So let's check sec challenge level 2.1. We see that there is no canary. However, it is a PIE binary. And let's say I want to throw GDB at this and see this transition going on in this binary. Well, I'm interested at the break on read. So let's do a couple things. Let's make sure I don't have a do.py. Oh, I have no camera. I can go over here. Make sure this works. Good. All right. We'll do our boilerplate. Make sure that's big enough. User bin end Python 3 from pwn import star context arch equals AMD 64. P equals process. Hopefully at this point we've kind of fallen into this pattern now where we have done this enough times. We've probably seen it for a while. And then I like doing GDB debug. One of the things that I did last week to kind of improve my workflow was I passed a second argument to GDB debug. This is where I specify a GDB script that I want to run. So in this case, I'm looking at IDA. I'm interested in what's happening right here at read. So I could say break on read, continue, and then give this a go. So we'll chmod plus x do.py. We'll run our do.py. This fires up GDB, and I'm immediately at read. And so I can fini, we can give it A, B, C, D, E. I think it took 5 characters. I'm now outside of read. I should be able to, I can't disassemble, and this is because this binary is stripped. Question from Twitch. Is GDB script the second argument? Because they always specify it by name, but they guess they don't have to. The answer is yes. So the first argument here is the binary or path, the thing that I want to execute. The second argument is the GDB script. This is true for gdb.debug. I like doing GDB script as a multi-line Python string here. It's a bit easier than trying to cram this all in one line and read it right to left. But now I'm on the other side of read. I can't disassemble. The reason I can't disassemble is GDB doesn't know where it is. Question from Twitch. What does P interactive do? So P interactive ties standard out of the challenge to this terminal so that whatever the challenge says gets spit out up here. And then anything that I type up here and it hit enter or pass in at the terminal gets read in by the challenge. So if I do this do.py again, we broke on read, I fini. Right up here now, the challenge is waiting for input. And so up here in my top left window, I can say A, B, C, D, E, F, hit enter. That then gets passed into the challenge. And what the challenge is printing out, I get to see up here. So P interactive is giving me that. And the second thing, which is why this is super important, I'm going to comment out P interactive. If I just do my gdb.debug, we see GDB starts up and then it goes away. In my output here says, hey, we started this process and then it's done, it's gone, right? We stopped this process. We started a process and then we stopped it. Well, that's not very useful. This weird behavior is happening in my left-hand side is when I run my script, the script is going to exit, my Python script is going to execute all of these instructions. And then it gets to the end of the file. There's nothing left for my script to be doing. So my Python script exits, right? We've ran all of the code in the Python file. When Python exits, audio quality drops significantly. My AirPods connected. I saw this here. Let's see. Oh, I have 2 audios. Okay, let's do this. Is this better? Going once, going twice, going 3 times. All right, we'll give this a moment. You'll tell me it sounds still echoing. Sounds the same. Okay, so you don't like this one. You do like this one. I don't know which mic is the good one. We'll go this way. Is this the happy one? You get one or the other. I just get no, no. This is then you get this one. There's only two inputs here, so like I'm not messing with you. This one is still bad, but okay. All right, we'll go with bad, but okay. Nobody knows what happened. OBS is a mystery. I agree. So my Python script here finishes executing all of its code. And when it exits, it in the Python is going to clean up this process because Python feels that it has ownership or responsibility for this GDB process. And so when my script exits, it kills the process that I'm debugging. By running P interactive, Python now has a job to hang out
as long as this process is alive. And so it's a good practice, in my opinion, to always end your scripts with p interactive. Like it'll just save you from weird behaviors of things that you're not thinking about. All right, so I can get into read here. We can fini. I can give it A, B, C, D, E. And then I could step through this. And let's display RBP minus hex C. Can I display it as a string? I can. And so what we see here is CDE. So this looks kind of like my string. I'm probably a couple characters behind. What did I do? Minus C. I want minus E. There's my input string. I don't know how to do this. Delete display one. Yes, two, three. Cool. So I'm keeping just this display in my GDB. As I step through, it should, unless Jeff is eating everything. Jeff could be eating things. It displays my string and kind of the state of it every time that I hit a pause point. I can also do that manually with x/s. So I could step through, look at it, step through, look at it. And we see my string is being manipulated, right? And so you can observe these things happening as well dynamically. Now, I managed to set that breakpoint because I knew that there was a read. But what if I want to break somewhere where there isn't a convenient syscall for me to set a breakpoint? Like, what if I want to break after this read? And so in my script, let's automate the passing of A, B, C, D, E, whatever. I want to break right here. We see IDA says this is at 14B2. That corresponds to this assembly instruction, but I actually want to go a little bit before that, which is going to be 14AE. I'm just looking at this little information bar down here. Now, somebody in Twitch chat says something about breaking on PIE. That was something that I believe Michael showed. Jeff and I guess pwn.debug has similar functionality. However, that doesn't work well with this type of a workflow where I'm using gdb.debug. If I want to use gdb.debug, I really want to deal with things in this GDB script field, right? And so what I can do is I can recognize that when I start a PIE binary with GDB, which is what's happening right here, the address, let's actually just see that, do.py, boom, VM map, the base address should be randomized, but it's not, or sorry, should be de-randomized by GDB, but it's not. And that's because this binary is setuid. And so we can actually pass in a couple more arguments. We can say setuid false, ASLR, I believe it's ASLR false. If we pass both of these arguments to a process or pwn.debug, and then we VM map, the virtual memory space here, like where the base address of where we've mounted this binary, is now a constant value. It's all of these fives followed by 4,000. If I run this again and we take a look at the base address, it's the same thing. And so this is a constant memory address that I can refer to as the base address of this binary, like where it's being loaded in memory. If I am working and I have a GDB init file, I can declare a variable in my GDB init that I always want to use. This lower stuff here, I wouldn't worry about. It's kind of like special edge cases. But these top three lines in my GDB init are probably something that you may want to consider including. The first line, make sure that GDB always shows us Intel syntax. The second one creates a variable that I can always use named base that corresponds to the base address that GDB will use by default when de-randomizing the base address of binaries. And then this third one is importing Jeff, which you hopefully have already decided you want to use. Now, why do I care about this base global variable in my GDB init? Well, that's because over here in my GDB script, I can now reference things relative to base. What IDA is showing me here, when IDA says 14AE, this is the offset from the base address of the binary. So I can now set a breakpoint at base plus OX14 AE. I probably need to give it a star because this is going to be an address, not a symbol, and then continue. Assuming that I'm doing this right, we now are at that address, 54AE, and in this case, it was 14AE, right? And that's because the base address, which we can just print base here, uh, already has something in the thousands place, right? It bases at 54,000. And so 54,000 plus the offset that IDA tells me allows me to break at any location inside the program without having to know the symbol. All I have to do is find the functionality that I'm interested in. Like, let's look at the assembly that's related to this if. Here's a jump not zero. I want to break at this jump not zero. IDA says it's at hex 14F0. Well, let's take a look and get GDB to go right there. Boom. Where am I? F0. I'm at the jump not equals. That corresponds. Why does this say jump not zero? Jump not zero, 14F0, 14F0. Okay, so IDA is doing something that's a little bit different here. But this is IDA interpreting this instruction. You say it's the same instruction. Jump not zero, jump not equal. Like, yeah, it's the exact same mnemonic. Yeah. But it's displaying it as a different um letter pattern, right? And that's just the choice of the tool. But I am at that same spot. And so I don't want people to think, hey, GDB is like the only correct tool and I should only be looking at assembly. I can use a static tool like IDA to reason about what's going on or decide what is an interesting place for me to inspect in GDB. And I do that by fixing the types and naming things so that they make sense here in IDA. And then I can use IDA to find the exact spot that I'm interested in and be targeted, like do precision strikes with GDB at the places that I want to dive into. Now you can use both of these tools kind of however whatever in whatever way makes sense to you, but it's definitely a mistake to go 100% gung ho on one approach over the other because sometimes a static tool will be more helpful and other times a dynamic tool will be more helpful. Does anyone have any questions about how we can kind of deal with that? I'll give it a moment. Give it a moment for the um, Twitch delay, 'cause there's always the old Twitch delay. So I'm not seeing any questions there. You do have the ability, if you watched Michael's lecture, to rebase the numbers in IDA, so not make this be based off of 0 and make this number match GDB. Personally, I just would rather leave IDA as an offset from the base and then deal with reasoning about it this way when I'm using dynamic analysis. So I've got about 5 minutes left. I spent way more time on this than I thought I was going to. Does anyone have anything you want me to try and cover in the last 5 minutes? If not, I will run a little bit late since I'm not in class and holding anyone hostage. And I'll open at least one of the CTF archive binaries that somebody said, that somebody suggested, whatever the first one is. I'll check this list. And if I don't know how to do it, we'll figure it out together. We'll solve at least one binary. All right, I'm getting nothing from Twitch, so let me see what the first suggestion was. Somebody says Patriot CTF 2022. I'm looking for something called string cheese. This is not meant to be an insanely difficult reverse engineering binary. It's hopefully one that is or makes sense to us. Let me find CTF archive. I'm looking for, we said Patriot CTF. See if I can search this. Patriot CTF 2022. String cheese. All right. Our hint here is I haven't had string cheese since elementary school. It says use flag check to input the flag you get from the challenge to get the actual flag. So there's two things that we will try and do since I have no idea what this is. The first thing that I prefer to do is just run the binary and see if this thing makes any sense. It just says reverse engineer this binary to find out the best Valentine's Day gift. Okay, can I echo something into this? No. And if I give it arguments, does it do anything? No. So somebody says the author is their long lost twin. That is pretty cool. Challenge authors are cool people. So your twin sounds pretty cool. Someone says they thought of me when they saw their nickname or thought of that person. Nice. Okay. So poking at it didn't make a lot of sense, right? It's clearly not like just calling read or what was this thing called in challenge cheese, um right? It's not blocking, it's not immediately obvious playing with it. Now I could just try and GDB this thing, and I'm assuming that there is a main function. Okay, there is. Main is going to call printf. Okay, I'm not entirely sure what's going on here. I hope this isn't a format string exploit, uh, because we haven't talked about those. But let's also take a look at this in IDA. We're going to go fire up IDA, take a look at it, see if IDA is telling me anything that wasn't immediately apparent from that assembly that I spent like 3 seconds looking at. We'll hit tab. Hopefully, we get something interesting. We really don't. Huh. So it just says reverse engineer this binary to find out the best Valentine's Day gift. Hmm. Okay. Twitch says, hey, maybe printf is hiding something. So I'm assuming that this printf is libc's printf. It's going to call printf. Looks like that does go off into. Oh wait, why do I have a main function here? Hmm, okay. Once I'd had this once in a CTF. Sad. Hmm. Starts at, there's a comment here. Starts at 1199. Well, that just gets me back up here to main. Oh, wait. This is some load instruction, and there is a flag hiding here inside the binary itself. And I got a Pico CTF. Is that Pico CTF? DCTF? I don't know. I have no, it's Patriot. I'm Patriot CTF. Patriot CTF string just hiding here in the binary in the read-only section. Would I have gotten this with GDB? I don't know. But we saw this right here. That's definitely a flag, so we found it. I got bamboozled by a decompiler. Yeah, I did. So I was relying on the decomp, right? And the decomp said, hey, this value isn't really being used by printf, it's not being returned, and so it hid it from us. But when we used the same tool and went back and looked at the assembly in IDA, we see that the flag is being at least accessed in this main function. Let's see what we would find out if we GDB'd it. Like when we GDB'd it, my first thought was that we'll disassemble main. Yeah, somebody says the audio is not happy, but I don't have a good answer here. I can bring myself down a little bit. But all I see is this when I look at could be the internet. The internet may be going in and out at my not in and out, but uh, acting a little funny at my location. So we just see these constants being loaded, and one of them is being print. Printf is being called. Printf, if we were to check the man page, the first argument is the format string, which is RDI. I then say this is RAX, which is this address. GDB does show me this, and so I would like examine the string here. I would see this. It would be very unusual. It'd be very unusual for me to go here and start examining every string that is in a binary. Like I wouldn't do that inside of GDB. Right? Something that I may want to do. I wasn't particularly inclined, and I don't think it's relevant for a lot of the Pwn College challenges. But there is a command called strings that you can run, yeah, uh, on a binary, and that will show you all of the strings that are there. And we do see that that leaks out this value. So I was able to find the flag, enter the flag. Okay, I get my Pwn College practice, right? And if I did this in real mode, I would be able to copy that and paste that in here as the flag. Right. So we were able to find that three different ways. I think one of the takeaways from this challenge was definitely to not just assume that the decompiler's higher level language is telling us the truth. The second thing that the person suggested, since this one didn't take too long, was Patriot CTF 2022 Crack Me. So let's see if we can find that one. Oh, it's right below here. Boom. Crack Me. Says this program is password protected and I can't figure out how to crack it. Can you help me out here? So we'll take a look. All right, Twitch. What tool do you want to use first? You want to take a look at IDA, GDB? You want to run strings? Let's do strings. If strings makes this thing fall out, then that um, is a sad day. We'll run strings on crack me or challenge crack me. And I'm looking now for this pattern, which is not. I see some interesting strings like congrats, you found the right password. This is kind of interesting, but I don't see anything that looks like a flag. Somebody else says L trace. So we can use tools like L trace and S trace. Hopefully you messed around with these type of tools in 365 a bit. I'm going to sudo S trace this crack me. It reads something. It writes out that this is incorrect. Okay, that doesn't help me too much. Like I get to see that this read call happened, right? It's reading from standard in and it's writing out. Somebody says use ltrace. Let's see if ltrace behaves. It's calling f gets on a password. Okay, there's a couple things going on now. So here's my ASDF that f gets is triggering. Ltrace is like strace, except strace traces syscalls, ltrace traces dynamic library calls. For those that are unfamiliar. So I see here is calling fgets to get my password. It is getting the string length of it. It's then mallocing something, and it's checking the length of some weird looking string. Not entirely sure what that is. And then we have a string compare with this weird thing and another weird thing. Now I entered 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. How many bytes is the second thing? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. So it looks like it's not even the same length, which is interesting. Somebody says it looks like it transforms your password and compares it to a constant. Yeah, we have seen this pattern before, right? Where we pass in some input, it gets mangled, and then there's a string compare. And so we've done everything except for the two tools that you will probably be driving your reverse engineering process, which would be IDA and or GDB. So let's open up IDA here. I'm going to go IDA first. Honestly, the static analysis tools are great for that kind of high level view, that 10,000 foot bird's eye view. And so we'll double click the file, we'll hit tab. Somebody says I opened flag check by accident. They are 100% correct. So let's try and do it the right way this time. What I want to open is crack me, not flag check. Okay, we tab. IDA says, here's libc start main. We go into main. Looks like we've got a couple things on the stack, including a 40 byte character array. Now, I can't trust that this is really 40 bytes in length, but maybe IDA is getting it right. And the IDA is guessing the length of arrays based upon how the memory region is used, as well as how things near that memory region are used. And so if this is at let's see, RBP minus hex 30. I want actually to show this as a, will you let me do that? Come on, Ida. You won't. I want to make this 40B hexadecimal, but I can't. The things that I want to make hex, I can't. That makes me very like very sad. So 40 in hexadecimal is 28. And so 28 bytes after this is a pointer that is being used. Right? This is being used and it's being used as a pointer, like we're calling free on it. And so I would trust IDA that this is at most a 40 byte character array. I think IDA got it right this time because it's saying that 41 bytes after this, there is a pointer and there's a region of memory that is being used as a pointer. And I verified that by figuring out what this length is and then looking at what the layout of the stack is here. So I trust IDA there. Now, I this pointer is 0, v5, I don't know what it is, but it is 0. We call some function that takes s, a2, a3. S is, I'm going to change S to be buff because that makes sense to me. So I hit N. I'm going to change this name to buffer. All right. I'm interested in this first thing that is buffer. It's going to take A2. Do I know what A2 is? Okay. A2 is the char star star of main. And if you've written some C programs, you would know that the second argument to main, typically the first argument is argc, the second argument is argv, the third argument is envp, the environment pointer. All right, and I'm just assuming that because we're calling main, and that is what these three arguments are. I don't understand why IDA didn't know that, but I can certainly change it so that it makes sense to me. So now that I've named these, and I have an idea of what's getting passed into this function, let's go in and see. Okay, so this is asking for a password and then calling fgets. So let's rename this. And we're going to say get password is what I'm going to call this thing because why not? This is calling fgets and then returning the value of fgets. If I don't trust that, we can always check the man page and make sure. The return value of fgets is in fact a character pointer, which is what we see here. And get password is taking one argument, which is a character array. And I know if I hit escape and go back, this first argument is the buffer, right? So it's taking a char star, and this is the uh, buffer is what I want to call that parameter. Boom. All right. So now get password is going to prompt us for a password. Call fgets. It's going to, I need to make sense of this. What is this 32? 32 is size. Checking the man page here. Oh, I don't want standard in. I want to search for size. Fgets reads in at most one less than size characters from the stream, where the stream is the thing that's specified right here. So that means that fgets is going to read in at most 31 bytes into this buffer. This buffer is 40 bytes in size. We are reading in up to 31 bytes. All right, we're then calling string length on the buffer. So this is going to be, let's rename it. V3 is a silly name. We're going to call it buff length. Right, the buff length, I have my buffer, I have my buff length, that is the return value of strlen. This goes into the GOT, so the strlen really is strlen, right? It's not some custom thing inside of the binary. Now I have this mystery function. This mystery function is taking a buffer, the length of the buffer, and then I don't know yet what v5 is, right? It's just something that was set to 0. Note that this is being passed in with an ampersand, so it's a pointer to v5 that's getting passed into this mystery function. If we double click here, we should be able to dive in and see this thing. I want to provide this context in the function definition. So I have a buffer and then I have a buff length. So let's rename this. The types here are not making sense, right? Because my buffer that's getting passed in here is a character buffer. So that's a char star. So let's fix that up. This is not an int64. This should be a char star. And then I want to change the name. It is buffer. This second value here Somebody says I can't. I don't know if that's an old message or not. Tell me what I can't do if I can't do it. The second argument here, IDA says is an int 64. But when I look at buff length, this is a size T. And if we go back up here to where buff length is, size T, it's got to be, I don't know how big size T is, to be honest. I think it's 8 bytes. Old message. Yeah. So we go in here, and I don't know what this last thing is. IDA thinks it's a size T pointer, which is interesting. So now IDA has a bunch of ints that are local variables. So we're getting a little bit crazy here. These are all right next to each other. And and these are all freaking ints. Okay. One that thinks is an unsigned int. Okay. The We're going to set, where's V14? V14 is an array of 3 ints for whatever reason. Now, I don't know, this could be like one giant array. This could be a bunch of locations that are right next to each other. I don't know yet. I could change it. IDA would probably get grumpy. It might make more sense. It might not. I don't know because I haven't gone into the code of this thing yet. V19 here I see is being returned by malloc. So let's rename this thing, or not the type. Let's rename this malloc pointer. Malloc takes a size. This is A3. So I'm going to call this malloc size. It's malloc size. It is a pointer, so let's give it that. IDA thinks it's a size T char, which is great. Now this is A2. A2 is the size of my buffer, right? Because when we went back here, this is buff length. So A2 is being used right here. We're taking the size of my buffer, whatever I input, which is at max 31, plus 2, dividing it by 3, and then multiplying that by 4. And that is what is going to be in this size pointer. Okay, and this size pointer was this argument right here, which means that the size that's being computed is going to be this V5. I don't know. This is the weird malloc compute size, right? I don't know what it is, but I want to keep changing and renaming things as I learn more about what is going on inside this program. Okay. I don't quite understand why we're doing this math, but I will accept it. A2 we said was my buff size, or buff length, so let's keep that. Boom. To make that look a little bit cleaner. And so now it's my buff length plus 2 bytes divided by 3 times 4. So it's mallocing something that's going to be slightly larger than what I have. If malloc fails, it exits. Somebody says you don't know why, but it reminds you of base 64 encoding. That's an interesting statement. I'm actually not familiar with base 64 or encoding as far as like the implementation, and that's just because I've never looked at the implementation of a base 64 encoding. Um, but once we successfully malloc, there is a check if the buff length is less than 0. Okay, and we see this as a while loop. This is a value getting initialized and then it's being incremented. So I'm going to call this I because it's some counter. I can't use I. IDA doesn't like I. Fine, we will call you counter. The counter is initially 0. This is a post operation. So this V3 is old counter. Um, and we are accessing the int 8. What type does it think this is? This is an int. This is being cached as an int 8. So I don't like that this is being cached. Um, right, we're looping through every byte of the buffer. I agree. What I don't like, and this is one of the things that annoys me about decompilers in general. This isn't a bad example, but is the fact that this is a character array that it's casting to an int 8 and then storing that in an int. I don't know how it's being used yet, so I don't know the correct type. But I agree, this is, instead of V18, it's like, it's at least buff byte. It could be an int, maybe it's not, I don't know. If the buff length is less than the counter, we're setting something to 0. And this V5 is unclear what setting this to 0 does if my length is less than the counter. Otherwise, like, but this is definitely when the counter gets longer than my buffer. My default case, as I'm looping through here, is the counter V4 becomes counter plus plus. So this is next byte. Okay. So that means instead of this being buff byte, I'm going to call this cur byte. Right? I have the current byte, and then I have the next byte. And this counter is just being used to get me to hang on to these bytes. Um, oh, oh no, 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 no. This is next byte. This is like counter plus one. So let's name you next byte. Oh yeah, I already have one. This is next counter. Now I can name you next byte, right? Because we're incrementing the counter again, grabbing the second byte. This is still just next byte. We're just setting things equal to each other. So whatever, your next byte too. The buff length is still less than the counter. We have this other thing. Well, this is getting a little silly. I have next counter. Now I have next byte. Okay. So we need 3 bytes for whatever this operation is that it's doing. We did stop the silliness. This is next um, byte 2, because these are equal to each other. Why IDA is setting some, why we have it like an arbitrary thing here that is storing the same value twice. I don't know. Okay, what's going on here? Well, it's taking the current byte, bit shifting it by 16 to the left. It's taking next byte, bit shifting it by 8, and then next byte is being bit shifted by nothing. So we're sorting these 3 bytes into kind of their own order here. That would be, that's why this thinks it's an int, right? Because it's doing bit shift on it, and you want to bit shift on an integer. And so I'm taking all 3 of those bytes, combining it into V15. V15, I'm going to call it combo bytes, right? Because it's the combo of all 3 bytes being added. When these are being bit shifted, this isn't really addition. It's the equivalent as if I ORed them all together, because I think, isn't it? No. That's a byte. Yeah, a byte bit shifted by 8 is going to go 1 byte over. This is going 2 bytes over. And then this one here is the least significant bits. So I have the three of them. Now we're going to set malloc pointer. What is this thing? Is there just three different counters? I'm going to cross-reference this because I want to know what was this value when it started, right? This is some mystery thing now that's being used. And we see in the cross-reference up above here, it's initially set to 0. So I know its initial value is 0. And now I have some idea of how this V21 is being used. And so this is my malloc pointer counter. And this is malloc pointer index 1, malloc pointer index 2, and then I imagine there's a malloc pointer index 3. Right? It is a little bit verbose here, but I would rather be more verbose so that way it's clear what I'm doing. Okay, so then we take these combo bytes, and I'm going to take this bit shifted by 18 and it with 3F. Now the combo bytes bit shifted by 18 is going to give me, I think, nothing, right? Since this would be my highest order, and it is 8 bytes being bit shifted by 16. Okay, no, it would. But I'm not entirely sure. So let's like take a look and see what is going on here at this bit shift. So I'll put the cursor here, we'll tab. I'm interested in what's going on at this shift right. I'm going to use that IDA trick to see this happening. At this instruction, I know my offset is 1 to D8. College has decided I do not need to work on this. Let's modify our existing do.py. What am I running now? Challenge, crack me. And I'm interested in breaking at base plus 1D or 12D8. It wants some input, ABC, let's just do ABC. I think 3 would be the minimum. I'm now at this shift right, and we're shifting right EAX. Let's take a look at what EAX is. That is 616263, so that's my ABC. But note that it is, where's my EAX or AX? It is not in the same order that I typed it in because the first byte that I entered should be the least significant byte of the number, right? When I enter a string and it's read in, it should go from right to left. All right. Now I want to see what is the effect of this bit shift because I couldn't have a good mental model of it. I'll go next instruction, and then we'll take a look at what is in EAX. I have hex 18. Well, how did I go from, where's my EAX? ABC to hex 18. Well, I'd have to think about the bits that are involved and where is that intersecting here because bit shifting by 16 is 2 bytes. I'm going not by 16 but by 18. So this should be the same as taking like 0x61. I need a Python terminal. See if I'm thinking about this right. Is the dojo okay? Bam. My Python. I want to know what is 61 bit shifted by 2. Well, that's 24. And if I call hex on it, that's hex 18. So it's with its bit shifting the whole thing, the combo 3 bytes by 18, the resulting value 16 is dropping the first 2 bytes. These 2 bits are dropping the 2 least significant bits of my A. And so now I'm starting to reason about what's going on here. It's going to AND it then with 3F. Maybe these are magic constants. I honestly don't care. Hex 18, we can AND it with OX3F, at which point we now have 24 here. And so that's what I would expect to be the index here into this character array. And this character array is A, B, C, D, E, F, G, right? It's the alphabet. And so the 24th letter, there's what? This is chat. I think there's 26 in the alphabet. 24 should be a W, X, X. Oh, we're 0 indexed. It'll be W. Um, and so we are now mapping this to alphanumeric characters. Somebody said, have I looked at globals? I think I'm looking at a global right now. I'm looking at a read-only global. And so I now see, and this is that same pattern that's going on. This is 2 bytes plus a bit shift of 2. This bit shift of 12 is 1.5 bytes. And so if I think about what I had going on in GDB, if I were to take this value here, boom, can I paste it? Yes, I can. We can paste it and we can bit shift that by 12 and then and that with hex 3F. I now get 22. And so we kind of understand what's going on here is it builds up this malloc pointer. And then we're going to increment the malloc pointer count. And so we're grabbing 3 at a time. We're doing this bit shift. Ooh, where did I go? We're doing this bit shift of 3 bytes. Did the audio get better or worse? Did I lose my audio? I am not entirely sure. Okay. Once we've done that, we're going to, somebody says audio is okay. For I is less than whatever is V14. We cross-reference that. V14 is an array of, it looks like just 3 constants. It's 0, 2, and then 1. And then it's being used right here. So I'm going to call it the 0, 2, the array 0, 2, 1. And it's going to index, grab the number that is my length modulo 3. So whatever is left over from mod 3. And it's going to loop through these. This is pre-incrementing. It's not a post-increment. It's plus plus I, not I plus plus. We then go to that malloc pointer. Minus I minus 1. And we set it to decimal 61. Yeah, decimal 61. Okay, which is an equals. Oh, somebody said this looks like, and I'm starting to agree, right? Um, this definitely feels like base 64. For those that are unfamiliar, and I don't know the algorithm of base 64, but like it definitely looks like one. Base 64 is a way of echoing things into base 64. What it gives you is a string that is all printable characters. It typically ends in an equal sign, and it gives you a string that you can uh, then pass into base 64 to decode. Is it not decode? Oh, uh, base base 64 decode, and we get back what we started with, right? And so if you have something like a binary, and you need to, for whatever reason, copy it via text, it has a bunch of non-printable characters, you can utilize base 64 to encode all of those non-printable characters as printable characters, and then recover the original value from all printable text. It's one of the nice properties of base 64. And I agree, while I don't know how it works, that what appears to be coming out at the other side of this is a base 64 string. And it's going to return that pointer. And so I'm going to say that this malloc pointer is a base 64 um, buff pointer, right? It's the buff that comes in. This now points to something that looks like base 64. I don't know that that's correct. I hope I don't have to implement this thing by hand, but maybe I do. Hopefully it's not that crazy. Now, where was I? I was in libc start main, which calls main. We got the password. We looked at this thing. This thing, I'm going to not change the type, but change the name. Base 64. I'm going to just call it Chal base 64, so it's not confused with what it might really be doing. Because maybe it's not really base 64, but hopefully it is. I now have weird malloc compute size. This is not weird malloc now. This is the base 64 buff size. Cool. What type does it think this is? It thinks it's an int64. What does malloc take? Malloc takes a size T. If I remember right, this value is being used in malloc. And we can hopefully cross-reference it. Now, go into here, cross-reference it from this. Yeah, malloc size pointer is getting dereferenced. So this is really a size T star, since I know how malloc works. So let's change this. Okay, no, it is correct. It thinks it's a size T. It's only a star because of or a pointer because of that ampersand being passed by reference. So that base 64 buff size is in fact a size T. It thinks it's becoming an int going into this next function that I don't understand. What this is, it's taking pointer, but this pointer I know is the we'll rename this the base 64 val putter. So now this is base 64 and all this stuff. This is where the size is returned. Size of the base 64 buffer is returned. And then this is my base 64 pointer. Okay, now I have two more functions. This one here looks like it takes the base 64 pointer as well as the size. Let's fall into this thing. It has this A2. I don't know why it thinks this is a character and then an int. I'm going to believe that this is a size T. Tell IDA to leave me alone. Why? Size T A2 is a char. This isn't getting cached here. Do I need to change this? that's taking an unsigned int. Like, I don't get why it's casting a size t to a char to an unsigned int. This is like that weird decompiler nonsense. Because it's clearly a size t. That's getting passed in there. A size t or an int, right? It could be casting the size t as an int, but honestly, that's not a detail I need to fixate on. This next function here, what was a1? A1 on this thing is the base 64 val pointer, and this is getting passed as a pointer. Do I know that this is a pointer? So it thinks it's a void star. I'm going to claim it's a char star based on what we saw. That means that this thing takes a char star, not an int 64. Okay, now that didn't get all, that now looks cleaner. And the second argument here, I don't know why it still is doing this weird cast with an int. I'm going to let that hang out, but it's definitely taking the base 64 val pointer as well as the base 64 size. This is the character pointer, which I know is the base 64 buff pointer. This is the buff base 64 buff size. Cool. All right. We have this result thing that is doing this weird cast. I don't know how this is getting used yet. It's definitely a number. Does everything work if I just make you a size T? Does that make IDA happy? Size T result. What is the type of this? This is a size T. Everything should be a size T, IDA. Come on. But if we look here, it is using EAX, so it's 4 bytes. So maybe it really is an int. And the reason that I say that, this int, right, maybe, yeah, I just says deal with it. All right, I will deal with my mistakes. Because the reason I say that is this is dealing with 32-bit registers, so it's definitely a numeric that is 32 bits in length. Um, if the result for I plus plus, the size is result. If the result is less than size, but I is 0, then we break. This would just immediately break. I don't understand. Um, because my size is not going to be less than or equal to I. My size is always going to be greater than 0. Um, somebody says it just iterates over the base 64 buffer. Well, the decompiled code wouldn't do that. I equals 0, we start firing on this thing. If I is greater than or equal to result, where result is my buff size. Like the decompiled code doesn't iterate over it because I would immediately bail on this. I isn't greater. Yeah, if I is, oh, if I is, okay, yeah, I can't read. Silly goose. If I is greater, we break. So we are iterating over this, and I just can't do basic math. Okay, so then we're iterating over this buffer pointer, the base64 buffer. We're going to set it equal to whatever it was, plus 20 modulo 94 plus 32. And we're going to do that to every byte. So I'm going to call this Crangle. That sounds like a good name for whatever this thing is doing. It is crangling our bytes. All right. This is crangling the base 64. I now have one more function. Um, and this thing is unknown, but I know it's taking the base 64 val pointer. It is copying some constant here, second the string length, right? This is S is now magic constant, which I'm guessing is my goal. Um, we compare goal to A1. A1 is that base 64 value. So let's rename this. This is my base 64 buff pointer. What is V1? Side is the stir length of goal. So we'll call this thing goal length. All right. If my crangled base 64 looks like this, then it says, congrats, you got the password right. Otherwise, the password is incorrect. All right. So we did I'm going to name this thing validate. Seems like a good name for this. And so we went through this program function by function, line by line, variable by variable, and we're able to reason about what is going on in here. What are these variables? What do they do? How does it work? The one thing that we made that was an assumption was the base 64, whether or not this is true base 64 or not. So let's see if we can suss out if this is real base 64. What I'm going to do is I'm going to look for where this child base is called. I'm going to set a breakpoint right when this is returned. This is at 15AA. 15AA. And I'm going to send it just 3 bytes because 3 bytes seemed to be the minimum for what we had going on there. Oh, I need send line. So it was blocked up above until I hit enter because it's calling fgets and I didn't read the man page for fgets. All right, cool. I'm done with this call, which I know is the child base 64. Right, I learned that over here in IDA. GDB doesn't retain that information. And what I'm interested in is what is in this pointer that's returned, right? RAX is the return value. And when we looked at this child base thing, it returns the base 64 val pointer. So I really want to see what is the string that is in RAX. And I get this right here. If I find, let's do bash, so I echo that value into base 64-D, I do get back my ABC. I'm not saying this is conclusively enough for me to say this is 100% a base 64 implementation, but it's good enough for me. I believe it's base 64, right? If I wanted to 100% prove it, I'd probably try a couple more values and make sure that this is flowing back and forth. So what that means is I have this constant that I want. Let's see if I can get this. Copy. I'll grab it from the old clipboard. Let's, I need, my goal is this, and I need to work backwards. If I work backwards from where I was here, get the clipboard gone. I need to decrangle. So I need to write a function that decrangles this, because this would be minus 32 modulo 94. So let's make goal a byte array. And then goal is, hopefully I'm thinking about this right. Goal is going to equal x minus, where am I? What was Krangling doing? Where's my Krangle? Krangling minus 32 modulo 94. I think I can do that. Minus 32 uh, modulo 94. Oh, and then it's adding 20. Am I thinking about this right? I'm going to reverse this, then this modulo, and then I'm going to subtract 20. 4x in goal. Call it the K goal. This K goal looks like something. And then let's change this. So the K char goal is going to equal char of x for x in K goal. And then let's look at K char goal. Oh, not CHR, CH or CHAR. Okay, so it doesn't like that. Somebody said they don't know that modulo can be reversed. Yeah, this is why I should learn some crypto. So somebody that knows crypto should chime in here and be like, here's some math. Um, Stating the value, adding 20, modulo it. Okay, so I definitely subtract 32, and then I subtract 20 in modulo. So is it really this? Like this should pop out if I'm doing it right. If this is a reversible, there we go. If this is a reversible operation, I should be able um, to produce a. Does it think this? Oh, I made it all characters instead of bytes. Yeah. Can I P8 turn this into a byte? This should all be numbers. Don't do that. From pawn, import star. Okay, that kind of looks like base 64. Um, Subtract 32 and subtract 52. One of those will fit. Uh, what did I have before here? 52, 32. Yeah, I'm close. You're saying 32? Because this should come out as a base 64 displayable string. So the fact that I have like this hex 16 does not bode well. It's definitely not minus 32. 52 looks so close. Because then I should be able. So there's two options. Either 32 is subtract or either 52 is subtracted, and you can't know which. Oh, are you saying okay for each position? Well, I can know that these non-printable characters are um okay, def. I can't do this now in a pretty looking thing. Yeah, if they're ugly, then I need to add 32, right? So from string import, I'm going to say ASCII, I think. I need to confirm that. Let's bring up Firefox, Python, string. There's ASCII letters, ASCII lowercase, printable. I am saying I want printables. So import printable, and we will do one more here on kgoal. Say kgoal equals x plus 32 for x in goal if x not in printable. What is this? In string requires printable should just be a giant string. Oh, and these are bytes. Okay. I need to turn, this is Pythonism. Can I just use, just want to use a range? I don't want to use a range. I want to be cool and use printable, man. I need to turn printable into a byte string, which would be, because that's all numbers. So that would be U8 of X or of Y, U8 of Y for Y in printable. And we'll do a comprehension in a comprehension. No, I get it wrong. You can just cast it. You can't cast that. Okay. If I do U8 of Y for, can you? Bytes of printable? See, you're just trolling me. Of course this works, as it is clearly not working. I need to specify encoding. I do need to make it a string. Okay, I'll take that. If not in the bytes of printable encoding Latin 1, then I don't need to do this. Uh, okay, so I can't do that check there because that's going to filter def uh, printable check, whatever, X. And this will say if X is in bytes of printable encoding Latin 1, then we'll return X plus 32 modulo 94. Otherwise, we just return X. That way we're always returning an X, and we will call printable check on X for X in goal. Oh, that's because I'm using kchargoal. I want kgoal. Okay, what the heck does kgoal look like? Kgoal. Okay, kgoal looks pretty real. Can I pack kgoal and then size equals all? No, because it's a list. Um, I pack an int. I'd want to unpack kgoal. It doesn't like that. You want to just bytes it, okay? I'm scared of things like that. Bytes of kgoal. Okay, that is very ugly. Should be plus 20 because you're saying I either do 50 or 32. You have your if the wrong way around. Oh, yeah, 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 yeah. If it is a printable, then I uh, 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 one of those will fit. Then so I need this is subtracting 52. So then if it's not printable, then we add 20. That looks like base 64. Okay. Let's import base 64. There should be base 64 decode of whatever this thing is. Really? Base encoded. It's going to equal bytes of kgol. How do I use base 64 decode? What do you want? Input output? Oh, it's B64. Decode of base encoded. It's all for naught. Base 64, B64 decode. That's what I'm using. And I'm using it on base encoded. Oh, it's grumpy because of that. Let's strip the Q's. And you need one more. Can't be a multiple four. Okay, whatever. So me. Base encoded is base encoded. I can strip Q, can't I? Encoded strip Q. All right. And then we're saying base 64, B64 decode, whatever A is what you say. Invalid. Number of characters 29 cannot be one more than a multiple of 4. Mm. Mm-mm-mm-mm. So there's this, which is kgol. The Q needs to be an equal sign. Okay. Let's replace, no, let's not do that. There could be a Q in there that I actually care about. We'll strip this and then let's append, you're saying equals equals. 29 cannot be a multiple of 4. All right, what is the length of A? Make sure we're not completely 44. We're so close. What is base encoded? All right, CTF close. You always add more equal signs. That's what you say. If this QQ, you just want to add equal signs. Okay. Like once you've added 4 equal signs, this has gone too far. We've covered every possible multiple of 4. Invalid base. Yeah, so the statement there on Twitch is that the base encoded here is doesn't look quite right. And so I'm doing something wrong right here, right? Because we would expect this to end in equals and not this QQ. It's all printable, but it isn't quite right. Saying maybe the printable trick isn't covering it well. I don't know what is a valid base 64 character. I know it's all printable. Does it say? Data is described for the base 64 alphabet in RFC, blah, 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 blah. Oh, you know what I should do? I should just grab what it is using in this thing in child base 64. Because the only possible characters in this thing that are allowed is whatever is right here, right? That these are the valid values. So that's what I get for trying to be clever. And where'd my terminal I was working out of go? Instead of using printables, we're going to call it B64 vals is going to equal whatever this is. And printable check is not going to check for this. It's going to check if X is in B64 vals. We'll make this a byte string. I think that'll make Python happy. That looks less happy. Because I'm getting this. Somebody says, "Are you shifting characters?" Oh, you're right. I did. I don't know how base 64 works. And Twitch chat said, and I just like blindly listened, that this I don't have to worry about. We just call this whole thing base 64. Let's ignore kind of what's going on here. So I'm not doing any of this bit shifting. Um, I'm just treating it as base 64. And the reason I did that was because we could pass ABC into this and we'd get ABC out. Yeah, it's someday, which is still saying it's part of base 64. So I'm not doing any shifting. The thing that I'm failing to account for here is the crangle. It's in the crangle. You call it wrangle? It's not wrangle, right? It's cooler than wrangling. It's crangling. I can't reverse this because I can't math. This is like some simple modulo math. So we are taking this, setting the byte to be whatever it is, plus 20, modulo 94, plus 32, which to me, as a non-math person, is the original value minus 52 modulo 94. I I don't know that that's true. And then Twitch chat got me on this weird track, but that's what I'm doing right here is minus 52 modulo 94. You're saying it can be all values between 32 and 52. You're I don't think that's true. It's a character value that is a base 64 character plus 20 modulo 94 plus 32. Mm, Like I've read this whole thing and I'm stuck right here because I'm too burnt to think about math. If you modulo 95 with 94, you get 1 plus 32 equals 33. How would I reverse that? Well, I would say I have 33. Where's my terminal? Let's see if this all checks out. You're saying my output is 33. What I'm doing right now is I'm subtracting 52, and then I am moduloing that whole thing by 94. And that gives me 75, which is not what I started with. Okay. Um, so can I, if I need to undo this, oh wait, you say that's correct? So it turns out my math does work. I am thinking about math correctly. Okay, so if I'm doing math correctly, then where's my miss? I'm right here. We're done with printable check because you say my math is great. I get this nonsense. Now you're questioning my math. Yeah, you said that my output's 33. I have 33 minus 52 minus mod or 33 minus 52 modulo 94 gives me 75. Isn't the value 32? So modulo 95 with 94 in the brackets. There's 33 minus 52 here, and you're saying I'm not sure what you're asking. This is modulo 94. Isn't the value 32? Um, yeah, plus 20 modulo 94 plus 32 in the brackets in my math. I have the numbers 33, 52, 94. And that means 75. Just I'll forward do it. 75 plus 20 modulo 94 plus 32 equals 33. Yeah, like I'm going back and forth on this thing correctly, right? Like I was good here, but I would expect this right here to be something that I could base 64 decode. And I am pretty sure. What? We just assumed this was invalid. This did successfully decode, which means this is my input. We just assumed that that was garbage, therefore incorrect. Password was incorrect. Okay. Still not there. Where do I want to break? It did decode, which is kind of cool. I care about this string compare, which is happening right here, 1538. Okay, let's examine the string in RDI. Let's examine the string in RSI. RSI. Yeah, it's definitely not the same string. Um, See if I can decrangle it. Oh, but I'm starting from the goal, right? There shouldn't be decrangling. Oh, right. I have the goal because I pulled that out. The last thing that happens before we are doing the comparison, right? The comparison compares a crangled version. When debugging, you can check if you decrangle correctly. Okay, so you want this. I'm at the super awesome spot. I'm going to print RDI or examine the string at RDI, examine the string at RSI. I think RDI is my happy value. You want me to decrangle this, and it should be a base 64. Mm, This should be the same thing as this, which it is, right? So I have my goal. So the first byte should be 9, which is hex 39. The first crangled byte is a 9. So I need to recrangle. Oh, you want me to decrangle, recrangle? Okay, decrangle, recrangle. All right, this is my decrangle. So I should be able to say, call it the recrangle is going to equal, uh, what's the Krangle operation here? Plus 20 modulo 94 plus 32. X plus 20 modulo 94 plus 32. 4x in Kaggle. And then we'll print the goal. We'll print the recrangle. The rectangle. The rectangle. Good day, good day, good day. Good day, good day. Why? Oh, there's another thing down here. And we want to bytes that. Oh, can I do this? I'm saying the decrangle good. We decrangle, recrangle, and we get back. I don't want to brute force base 64. I'm so here. I have all of the pieces. We're here. I can decrangle and recrangle. I'm a crangle master. All right. I'm crangling so hard you don't even realize it. So if I can decrangle and recrangle, then I need to base 64 decode Kaggle, bytes of Kaggle. All right, I have something. Is that the same thing I just tried? It is. Make it anything? Did it say happy or sad or nothing? You read the new line, the password was incorrect. Yeah, I was hitting Control D to not pass the new line. Hmm. I feel like we got there. Password was incorrect. Why? I'm the master of the crangling. At this point, I'm committed. I'm committed to getting this. Stir length of the goal, it's the stir copy. I care about the stir compare. That's our break. That's at the stir compare. You want to look at the stir comp. New line. Examine the string, RDI, examine the string, RSI. It's so close. Where's my 9? We had this. Gosh, dang it. All right, I am running out of time. I can tell that I should end the stream. It's causing problems for everyone, and I've ran ridiculously late. So, um, hopefully this was fun. I'm going to try and finish this on my own, probably off stream. I need to get out of this room that I'm in. I appreciate everyone hanging out. It was funny. I'm glad somebody got some enjoyment. I will be back in class next week. It should be a good time. Thank you all. Goodbye. Good luck. And let me know what you're thinking on the Discord.